Hello everyone and welcome to this lecture. In the last lecture we have seen some applications of spectral theorem. In particular, what we did how to express the largest eigenvalue, how to express the smallest eigen in terms of ratio, okay, in terms of some ratio x transpose ax divided by x transpose x, and the maximum of this ratio will be overall possible x will be giving you the largest eigenvalue. The minimum of this ratio overall possible x will give you the smallest eigenvalue for any symmetric matrix. Okay, now continuing with the applications of more application of a spectral theorem, we will be now again coming back to the question we asked in the last lecture about what will be the number of walks of length k between any two vertices, and in particular here we will be mainly focusing on the number of closed walk of length k between, not between, because the closed walk is a walk which is the starting point and end point are same, and starting vertices both are same for a closed walk, and we want to find such walk. Okay, so yeah, so essentially what means is, suppose the graph is given to us, right, and there is some vertex I, a closed walk look like this. You go there, maybe you trace some again, some edges are repeat, and then you come back again, right? Similarly, I suppose this is of length k. Length of k means there are k edge, basically the walk is using k edges, okay, and then similarly there may be another walk, again it can be come back and then finally reaching here. So this could be, so how many possible such k walks are there? Okay, and we have established that this is indeed given by this number a to the power k, okay, then I comma I, starting and ending both at I. Okay, so this is the total number of closed walk at vertex I of length k. Okay, what about the total number of closed walk of length k? It's very straightforward. We will sum over all possible vertices. So this will be given by this. Now how to find it? Okay, I told you the eigenvalues makes our computation very easy. In particular this we can find a to the power k kind of quickly. Okay, so how can we write? So we know that due to spectral theorem, because A is symmetric matrix, I can decompose this matrix into V, then what was that, D, VD, V transpose, where V consists of all the eigenvectors corresponding to lambda 1, lambda. So let me write, suppose A has eigenvalues lambda 1, now let me here order them, okay, and corresponding eigenvectors may be V1, V2 up to Vn, and I am assuming them to be orthonormal. Okay, orthonormal. So every vector has a norm 1, the length is 1. Okay, very good. So now, and I want to, so basically what is this? This quantity is, yeah, before that a to the power k. So a to the power k is nothing but this, right? A to the power k is nothing but V. We have seen this, right? Right, very straightforward. Then this is nothing but trace of a to the power k. Basically this quantity is nothing but trace of a to the power. So let me write trace of this. So trace of, basically trace is nothing but the sum of all the diagonal entries, right? So basically I have to count. So trace will give you, in fact, the number of closed walks of length k, all possible number of closed walk of length k. Okay, yeah, but how to find it? How to find the trace of this? Now if you see it, let me open this. So this is V is what? So V is nothing but this, right? Vector 1, vector 2 up to vector, how many? Yeah, there are n. What is it? N I will be considering. Okay, drawing is slightly bad, but I hope you will understand this. So this is lambda 1, lambda 2, lambda n, this is 0, then again, so this will be transpose, right? So V1, V2 transpose, very good, dot Vn Very good, right? Now I can write this. This is nothing but you multiply this by this matrix is nothing but this. This is nothing but this, right? So there will be k, right? By the way, yeah, because this, yeah, okay, good. So now this will be nothing but lambda 1 to the power k v1. I'm multiplying these two things, right? And then second vector will be what? Lambda 2 to the power k v2. Go on, lambda n to the power k vn, and very good. And then this v1 transpose v2 transpose vn transpose. Very good. Now what? We know that trace of AB equal to trace of BA. Okay, this is a DIY for you. Prove that trace of AB equal to trace of, very 11th class, 12th class stuff. Okay, so just revise this. So that means, yeah, so basically, yeah, let me write the trace everywhere. I have to write this trace, right? Trace. Then this is equal to, sometimes I am writing capital T, sometimes small t, but I mean I have to be consistent. So suppose now onwards I will write small t. Okay, trace. So trace of this will be, yeah, so I can actually take it here, v1 this, v2 this, vn this, and then this matrix. So this matrix is nothing but lambda 1 v1, lambda 2 v2 lambda n vn. Okay, now things are very straightforward. Now trace of this is nothing but I have to care about the diagonal entry. So what will be the diagonal entry? What will be the first diagonal entry of this matrix, this whole matrix? If you multiply the first vector, first row with first column, this will give you what? Because v1 transpose v1 is equal to 1, so this will be giving you, okay, so let me write now, this will be, this no necessary trace here. Now I will directly write the expression of trace. So this will be, first quantity will be lambda 1 to the power k. What will be the second diagonal entry? Second row times second column, which will be lambda to the power k, and in this way this will be nothing but lambda to the power k. And we have established that the number of closed walk of length k can be calculated using the eigenvalues, basically sum of kth power of eigenvalues. Okay, so this is established. Now let us see beautiful consequences of that. Okay, so the first consequence is this: when k equal to 1, this will be giving you what? Lambda 1 plus lambda 2 up to lambda k, lambda n. I don't know why this is giving this, so let me add this plus, yeah, yeah, and this is for k equal to 1. So how many walks of length 1 are, how many closed walk of length 1 are there? Is it possible? So suppose you have started at vertex and then at one step you are going for, in order to come back you have to take one more step, right? So there is no closed walk of length 1. Okay, so this quantity is nothing but 0. I think you already have seen this expression. This is nothing but trace of adjacency matrix is 0, and trace is nothing but sum of eigenvalues. But now next thing is this. Okay, what about when k equal to 2? What about when k equal to 2? So what will be this? Yes, okay. Yeah, what will be this equation? So this will tell you number of closed walk of length 2, right? So basically this. So you start at vertex, this, let me again write this. There is a vertex high. What will be a walk of length 2? A closed walk of length 2. You are going and then you are coming back to the same edge, right? So it essentially is counting, it essentially is basically the number of edges this vertex will have, those many two length closed walk will be there, right? Those many. So this is one possible, this is another possible, this, right? So this is nothing but sum over, so this is degree of that vertex, right? So sum over degree of all the vertices. This is nothing but sum of degrees of all the vertices, and which is nothing but equal to twice the number of edges. So basically your eigenvalues can give the number of edges as well. Okay, so very good. And then next thing is so this is, remember when I was asking about that proof a to the power k will give you the number of closed walk all length k, of course II, right? Summation over all possible I. And towards the end of this lecture, I ask you how many triangles will be there. Okay, in a graph. Now hopefully you will find the expression for it. What will be this expression? Lambda 1q plus lambda 2q and lambda nq. Remember, this will give you what? Total number of closed walk of length 3, and indeed a triangle is a closed walk. So suppose this is a triangle is there at some vertex I. Okay, but how many times this triangle is counted? Or I mean C3 is counted how many times? See, this is counted. So see, for this vertex, if you see carefully, this is one closed walk at 3 of length 3. So this direction, another could be this one, right? This is also, right? And similarly, there are two other vertices, right? So this walk will also, I mean, this triangle will be also counted in a walk when we will take from this vertex. So I, j, k, suppose this is k, right? So there are 3 vertices, and for each vertex, this triangle is counted twice, right? So basically a given triangle, a given C3 cycle is counted 6 times. So this is nothing but 6 times the total number of triangles or T. Okay, so I hope, I mean, this is very straightforward. But what about lambda 1 to the power 4 summation over lambda I to the power 4 lambda I to the power? I mean, as you will grow this exponent, the structure becomes more and more, I would say, clumsy, or I mean, it's hard to figure out the proper structure out of that. Okay, so in particular, I asked you how many C4 will be there. Basically, how many such cycle will be there? Such cycles will be there. Okay, keep on thinking. Can you write the number of such cycle in terms of eigenvalues? Okay. Okay, great. So now let us move to another nice application of spectral graph theory. Okay, and okay, so and this is about the relation between diameter of graphs and eigenvalues. So I will be stating the precise result after maybe 2-3 minutes, a precise statement. But before that, let us see what diameter of a graph is. Okay, so suppose okay, so before defining diameter, we need to know what we mean by distance. Okay, distance between two vertices. So distance between two vertices I and j. Okay, the distance is nothing but the length of shortest path between vertex I and j. Okay, path we already know, right? We have defined this in very first lecture. Okay, path is a sequence of vertices and edges where obviously the edges are not at all, the vertices are not at all repeated, hence the edges will also not be repeated. Okay, so what? So, and there can be many paths between any two vertex, right? So for example, if I draw some graph over here. So suppose this is maybe one more, okay, yeah, 1 2 3 4 5 6 7, okay. Now, so what will be the distance between vertex 1 and 3? There are path of length 2, so which is this one, right, which is this one. Then there is a path of length 3, then there is again one path of length 3, right. So there are two path of length 3 and one path of length 2. So a shortest path, the length of shortest path we will call distance between those vertices. So vertex 1 and 3 at distance 2, not 3, okay. Now what you do, among all pairs, right, among all NC2 pairs, right, you calculate the distance between all these vertices, right, and then the maximum of that distance is called diameter. So diameter is diameter of a graph is the maximum distance between any two vertices, okay. So what will be the diameter here? What will it? So basically what you have to find the distance between every pair, so like 1 2 1 3 and so on, right, whatever the distance is, and then you find the maximum distance, so the maximum of, so whatever the distance here, so d1 2 d1 3 and so on, so maximum of distances, that will be your diameter. Now the result is this diameter, actually you can have one bound using eigenvalues, okay. So let me write the statement. It is a very, very nice one. So it says that the diameter of a connected, I am using the connected graph G is strictly less than the number of distinct eigenvalues of the adjacency matrix of G. Okay, I hope the statement is clear. It says that diameter cannot, in fact, it's strictly lesser than the number of distinct eigenvalues. Remember, if the graph has n nodes, there will be n eigenvalues, and out of those eigenvalues, some may be repeated, right? So we need to fix the number of distinct eigenvalues. How many distinct, and your diameter will be strictly lesser than this. Very neat fact. So let us prove this result. Okay. Okay. Proof. Okay. Proof is, suppose out of those eigenvalues, by default, let me call, that's a lambda 1, lambda 2 up to lambda t are the distinct eigenvalues, of A, where A is adjacency matrix. Okay. Now, okay, and for simplicity, I will choose the eigenvectors corresponding to these eigenvalues as normal vectors, right? Basically the unit vector. So suppose this is v1, V2 up to Vt. Okay. Now let us see the matrix which I will form using A and the eigen values. Okay. What will be this matrix? A minus lambda 1 I, A minus lambda 2 I, dot dot dot, A minus, these are the products, right? I would say, in fact, yeah, these are product, right? A minus lambda T I. Okay. So, in fact, let me first write the expression. So, what will be the overall expression for this? Okay. So, it will be nothing but A to the power T first, and then plus, then if I am doing it wrong, minus 1, then summation over, yeah, I equal to 1 to T, and here you're choosing this, and then yeah, I think I'm correct. T minus 1, correct, and you keep on going, and the last term will be, yes, minus 1 to the power T, and then you are producting all. This is product, I equal to 1 to T eigenvalues, right? Yes, I, and then you multiply by identity matrix. Very good, very, very good. Now there is a surprising thing here. The way I have written U in the very, very complex fashion, but indeed U is very, very simple matrix, the simplest of the matrices you have ever seen. What is U? Okay, so let us see what will happen if you multiply U with vector, suppose Vt. Remember, Vt is eigenvector corresponding to eigenvalue T. So this expression will give you what? If you just see this, the last term will be what? The last term I am writing it here. So last term A minus lambda T. Okay. So yeah. So let me actually complete this. A minus lambda 1 I. Okay. And then you are doing this product, right? So this will be nothing but. Now if you open this, so everything will be same here. So this is what? AVT. AVT is nothing but lambda T Vt, right? And this expression will be also lambda T Vt. Oh, this will give you 0. This will give you 0. Similarly, if you multiply this with any other eigenvector, this will also give you 0, because if you multiply these products are commutative. You can put this at the last and this one at the beginning. It doesn't matter the problem, because these products are commutative. Here AB equal to BA. In general, this is not true, but it is not difficult to prove here that these are commutative. Okay, but there is more better fact than this. The fact is, in fact, if you multiply U with any vector, it doesn't matter whether this vector is eigenvector or not. In fact, you multiply this with any vector in Rn, x belongs to Rn, this will still be 0. But why? Why? This is 0 due to spectral theorem. See, x can be written as linear combination of eigenvectors. Linear combination of eigenvectors, because these eigenvectors are orthogonal, they span whole space of Rn, right? So any x can be written as some alpha 1 times v1, v1 and so on, alpha n times Vn. Now, because these are eigenvector, this vector will also be, no, if you multiply this with this, right, x, ux, so you see that the expression will be like here, right? So again, expression will be like here, A minus lambda 1 t, and then, lambda 1 I, A minus lambda t I, okay, and then you're multiplying with this, okay. If you do this, sometime this will be V1 will be multiplying with this, which will make 0. Sometimes this will be making 0, because all these, if you multiply any vector to this expression, it is giving you 0, and x is nothing but linear combination of this, okay. So basically for any x, this will be giving you 0, okay. Now what is the implication of this? Basically the implication is every vector lies in the null space of U. Every vector, okay, every vector is basically nullity is full. The nullity is equal to n, because every vector is in the null space of U, right? So that means what? Due to rank nullity theorem, the rank is 0. The rank of U is 0, which implies, when can the rank of any matrix be 0? When all entries are 0. So indeed, this implies that U is 0 matrix. Okay, very good. Now we are just one step far away from proving this neat result. So basically, now this expression, the one, this is indeed equal to 0. So let me write this expression here. So this was AT. In fact, I can write in that term. So AT equal to, I will take this all terms on the other side. So this will be equal to summation over, okay, so summation over, yeah, lambda i's I equal to 1 to t, then a to the power t minus 1, okay. And because I am taking this, okay, so I can, maybe I will just do minus, it doesn't matter much. So minus 1 to the power t, same thing, I equal to 1 to the power t, lambda i's, product of lambda i's. Now what? Suppose your diameter, let me call it d, suppose diameter, so diameter, let me write diameter d is greater or equal to t. What will happen in that case? Okay, let me tell you what will happen. So the diameter is greater or equal to t, basically, so there will be two vertices in which the distance between them will be d, because diameter is the longest distance, so there has to be two vertices, distance is d, and in between there will be vertices, right? So this is some path here, right? Okay, there will be some two vertices here, any two vertices whose distance between them will be t, right? So suppose these are I and j, the distance between them is t, right? And the distance between them is not t minus 1, because the distance is what? Shortest path between, shortest path. So this is the shortest path between, so, and this is the length is t, right? Okay, so basically there is no path between I and j which is of length t minus 1. Okay, what will this imply? This implies this, that this guy a to the power t, there will be ijth entry here corresponding to this, which will be non-zero, because there is a path of length t. There is a path of length t between them. Okay, so that means in a to the power k, there is ijth entry. So suppose this is a to the power k, this ijth entry is not 0, because there is a path. There is a path between vertex I and these two vertices are distinct vertices. Okay, and the corresponding matrices here, right? All these matrices on the right hand side, if you see all these matrices, okay, these corresponding entries, because these are, the power, sorry, not this is k is not there. This is t. Okay, these are lesser than t, so there is no path of length t minus 1. So the corresponding entries here will be 0, and similarly dot, I would say 0. Okay, and remember in the last part there is identity matrix. In fact, there on the diagonal there will be a product of eigenvalues, but since we are talking about the distinct eigenvalues, so it will still be 0. Okay, so non-zero is equal to 0 plus 0, which is actually a contradiction. Hence, the diameter can be not at most, strictly lesser than the number of distinct eigenvalues. So diameter, so this implies the diameter is lesser than the number of distinct eigenvalues. Okay, so with this I will stop this lecture and see you in the next lecture. So thank you very much.